Thank you everybody for joining me today for this webinar on my company, Aerodynamic Solutions. The objective of today's webinar is to give you an overview of our company, the values and experience that we hold, also where we sit within today's turbomachinery design cycle. My name is Michael Nee. I'm product manager here at Aerodynamic Solutions. Also with me today is Bob Nee, who was founder and CTO of our company. I think it's best to start with our experience as a company. Prior to founding Aerodynamic Solutions, Bob was a senior fellow at Pratt & Whitney. And really, he was in charge of creating a design and analysis system based on CFD for commercial and military jet engines. Right? This basic building block, this CFD, had to be aerospace class. In other words, it had to have a predictive accuracy and a turnaround time so that it can be applied with confidence during the design cycle. Really, the only way to build aerospace class CFD is actually over a long period of time, developing knowledge, accumulating knowledge over many design cycles, working closely with designers, experimentalists, and aerodynamicists to make sure that this building block CFD, was validated to physics. After 30 years at Pratt & Whitney, Bob retired in 2003 to strike out on his own. But having done that, he took with him from his time at Pratt & Whitney certain values that we thought were requirements for really creating a CFD system that you could count on for turbomachinery analysis. The first value is to be independent, not only as individuals doing the analysis, but to make sure that from a predictive standpoint, that the CFD was without bias. And to do that, it really means that the software has to be validated to be true to physics and not calibrated to engine data. Now, this is very difficult because CFD in upon itself is a prediction. So how do you go about the validation process? And really, the only way you can do that is by spending countless hours understanding the root cause of differences between CFD and engine data. And the first thing to do is really throw out all of your biases and say, well, there are many sources of error when we do a comparison between CFD and data. And not all of them are CFD related or experimental data related. There are many sources of error, such as user bias, incorrect boundary conditions, or incorrect geometries. Including with that is differences between where experimental data is taken and how CFD data is taken. But the only way to really understand this is to have the experience doing it. And we have that experience because there are many scars over a career of trying to validate software. The last value that we have is a focus on designers. Okay, we want to make sure the designers can do what they do best, which is focus on designing turbomachinery and not the numerics of CFD, right? We also develop methods that work within today's modern design cycle, rather than focusing so much on predictive accuracy that takes so long that it can't be used. ADS focuses on creating methodologies that build confidence one layer on top of the next. Now I want to kind of talk about where our software sits within the turbomachinery design cycle. Here we have a flow chart of a typical design cycle where it begins with a mean line and streamline analysis. Here, a designer takes and develops an idea for what the number of airfoils, the velocity triangle, and the inlet and exit flow radius, inlet and exit radius of each row will be. They will then bring it into our software using those parameters to generate 2D airfoil sections that match those parameters, perform CFD analysis and a 2D simulation in order to eliminate as many candidates as quickly as possible. And then as you build confidence in those designs, you can stack them into 3D to form a single row analysis. You can then build more confidence by attaching more stages together. And then finally, to get even the highest level of confidence, you run complete unsteady analysis. This loop I call the turbomachinery tight loop. This tight loop is the major gate when we talk about the overall design cycle time. What ADS focuses on is reducing the overall time it takes to go through one of these loops. And one of these loops includes generating the airfoils, pre-processing or generating a good mesh for this analysis, running it, and then being able to analyze those results and determine what your next step is really quickly. Okay. So what is the software that we use to enable this turbomachinery design cycle? The first is ADS foil. That's our parameterized airfoil design tool that can be used within the design cycle. Next is our automated structure mesh generator. That's code wand. It's specifically for turbomachinery blading applications used during the aero design process. Next is our aerospace class flow solver. This is our validated software, code Leo, that is capable of handling both structured and unstructured meshes. And I'll go into a little bit about unstructured meshes later in the talk. Next is our graphical user interface, the ADS workbench. This helps simplify and automate the design and analysis process. Next are two services or enabling technologies. One is Cloud Leo, which allows you to get on-demand compute infrastructure from industry leaders such as Amazon Web Services. Next is our on-demand pricing model, which allows you to pay only for the solver hours you use. So now I'm going to take a little time to go through each of the software or technologies one by one. First, I want to talk about one of the most important parts to the ADS software suite, which is code wand. And that's our automated high-quality structured mesh generator. It's specific to the aero design process, and it's able to automate the process of generating multi-block OHH type meshes for both axial and radial machines with splitters. Okay, you can then take those blocks and then create efficient multi-stage simulations also within code wand. Because this is all automated, that process really simplifies the tight loop for the pre-processing step. Next is our aerospace class flow solver, code Leo. All of the technologies that have been selected or implemented within code Leo have been implemented specifically because they are best at matching physics. Okay, first, it's a density-based code and which employs the cell vertex scheme. It uses the finite volume approximation method, which means it uses distribution formulas for obtaining the second derivatives and upwind bias due to convection and propagation. Also, code Leo can handle 4 types of mesh elements, tets, pyramids, prisms, as well as the structured hex elements. It's an explicit time marching solver. It blends second and fourth order smoothing to reduce oscillations in the flow field due to shocks and transient flow. For convergence acceleration on structured meshes, we use the multi-grid approximation, the multi-grid method. And for unstructured meshes, we used our proprietary residual propagation method. Okay. We are able to handle time-resolved flow simulations using the dual time-stepping method. And for low-speed flow problems, we use the preconditioning method. Code Leo also implements a heat conduction module and a nonlinear harmonic balance module. Here are a little bit of the advantages of code Leo. First off, it's highly robust, meaning for many types of meshes, it can converge quite readily. Second, it has a low memory footprint. Because of the cell vertex scheme, the methodology is second order accurate even on non-uniform meshes, which means that it's highly tolerant to skewed meshes. This is important when we're talking about unstructured meshes. Code Leo is fast and it's been developed from the ground up to be HPC compatible. One of the biggest advantages of Code Leo, I think, is the integrated turbomachinery post-processing, which helps, again, speed up that tight loop by enabling you to get the data that you need as quickly as possible. So here are some applications of Code Leo. First would be turbine end wall secondary flow analysis or multi-stage compressor analysis. Next would be centrifugal compressor map generation and unsteady analysis with or without species tracking. Code Leo and Code wand can also be implemented together to do more advanced turbomachinery flow simulations, such as a combined fan, LPC, and bypass duct simulation. We call this a split flow simulation. Another advanced turbomachinery flow simulation would be HPT and LPT interaction with an intermediate strut. As I mentioned before, Code Leo also supports unstructured meshes. Really, we view unstructured meshes as being a requirement when we get to more complex geometries later in the design cycle. Right? We know that because of these complex geometries, a big portion of the problem of the time is consumed generating a structured mesh. And that's why it's important for us to be able to solve unstructured meshes. We have a partnership with Pointwise, and we're able to dump their T-Rex type meshes directly to our Code Leo restart format. Because of the cell vertex scheme and the fact that it's second order accurate even on these really highly skewed meshes, we can provide really robust solutions on unstructured meshes. Okay. Some applications of Code Leo in unstructured meshing would be for analysis of an airplane body or a rotating propeller. Some turbomachinery specific applications would be in the analysis, conjugate analysis of a high pressure turbine first vane. In this case, what you're seeing is a high pressure turbine vane with 648 fully resolved cooling holes. This was done with an unstructured mesh generator Pointwise. And if we had tried to do this with a structured mesh generator, it would take even longer to generate the mesh compared to even running one simulation of it. Another application of unstructured meshes would be coupling, for example, a unstructured volute to a structured centrifugal compressor stage. The next piece of software that I want to talk about is the ADS Workbench. This is our user interface. It has 5 major purposes. The first is to help you understand the software quickly by helping you create cases with a case generation wizard. Has integrated help in cheat sheets. Second, it can automate the post-processing by implementing 2D and comparative charting of the integrated Code Leo output, turbomachinery output. The ADS Workbench and actually our software is able to generate output files that are compatible with ParaView, TechPlot, and FieldView. Another important feature of the ADS Workbench is the ability to manage resources. For those of you who don't have an IT department who can implement a queuing and batching system, the ADS Workbench enables a very rudimentary queuing and batching system which is able to monitor your compute and license utilization and make sure that if you have a large number of simulations that you want run, that you don't have to wait for the completion of one before issuing the next one. The ADS Workbench will monitor when licenses and hardware becomes available and will issue simulations that fit within that utilization. Another capability of the ADS Workbench is for case management. You know, with the CFD simulations, there's a lot of data that's generated, and the ADS Workbench kind of organizes that for you and enables you to search for various pieces of data all within one case or one simulation or one project. Okay. The ADS Workbench also enables you to run the simulations anywhere. Okay, whether or not you want to run it locally on your workstation or laptop. If you have a cluster, you can use it to execute your simulations remotely. You can also use it to run it on the cloud. Okay. Lastly, and very importantly, is it helps automate those tasks that require a lot of user intervention. For example, compressor and turbine speedline generation, or target mass flow, finding a target mass flow, especially with a density-based code. Next is it has the ability to automate the process of finding or running to simulation to convergence and automating the design and analysis process for airfoils. And I'll go into that last one in a little bit later when I talk about ADS foil. Now I want to show you an example of how the ADS Workbench can help you generate those speed lines in the output. So not only does the ADS Workbench in the process of generating a speed line run the cases for you, but you know, with so many cases being run, the big problem is actually being able to analyze that data quickly. And the speedline generator will create a report which gathers all that data so that you can view that quickly. Here I have an example of a 4-stage axial compressor. This axial compressor is executed from choke to stall. A number of cases will be generated over a time period where the ADS Workbench will see what the first iteration of cases look like and then slowly increment towards stall, towards surge, so that you can get a good idea of what the actual range of the compressor is. Once it's done, it will generate this plot file. The first two plots, which are the total pressure ratio versus corrective flow and total efficiency versus corrective flow, give you an idea of the performance of the machine. Okay. Additionally, the total efficiency versus corrected flow has a little convergence tail, which enables you to see how credible each of the simulations are. Anything with a long tail means that it had trouble converging over some number of iterations and may be in the process of dying in this case. Okay, so now that you know the overall performance of the machine, the big question becomes, how can I improve it, right? And that's what the other plots are. When we talk about rotor efficiency versus overall efficiency, right? And then also when we talk about the loss buckets per row. And what we plot here are each of the losses for each of the simulation as a function of flow. And what we see quickly is, if we look, we see an outlier row, which is row 7. But also more difficult to see is another outlier row, which is row 5. So we know very quickly that we can target row 5 and row 7 as the limiters for the range of this compressor. And that really is the power of the speedline generator. You get all these results with a push of a button, and you can get it overnight. Now I'm going to talk about ADS foil, which allows you to use your basic parameters to define various airfoil types. For example, you can develop fan blades, high pressure compressor blades, low pressure turbine blades, or high pressure turbine blades. You can also use the ADS foil to define radial machines by defining a tip and hub section along a camber line. The real power of ADS foil really comes into play when you see it integrated with the workbench. Within the workbench, it has a user interface to enable you to see in real time how the basic parameters affect the shape of the airfoil. Okay, with a click of a button, you can quickly generate a mesh and simulate it all within a couple of minutes. At the end of the simulation, a loading file, a loading plot will show up, and you can quickly analyze the loading of the airfoil to determine how you want to change the shape. You can iterate in this design cycle very quickly, and that really is the power of the ADS foil generator. So now I want to talk about some of our enabling technologies. The first is our unlimited compute capacity on demand service, which is called Cloud Leo. A lot of people do not have the infrastructure in place to power, to cool, to manage a large cluster. And with Cloud Leo, it really enables a small company or any company to really get capacity on demand without having the burden of having to store or own all of that equipment. It's built on top of a secure architecture. We use class-leading infrastructure from Amazon. Amazon is one of the largest online retailers. I'm sure everyone has heard of them. They process billions of dollars in transactions every day. So their main purpose is for security. We build on top of their secure architecture our own levels of security. First, all cases are set up locally, meaning only the mesh is actually transferred over the cloud for execution. That mesh is transferred securely using 256-bit encryption. And then once it is executed, it will be monitored. And then once completed, all the data will be transferred back, again using 256-bit encryption. And the cloud infrastructure will be wiped clean and deleted. So nothing is left resident on the cloud. None of your data is left resident on the cloud. Okay. Additionally, with this method, you own or you are renting that compute infrastructure. ADS has no ability to see what you're running or how it's performing. That's not something that we have access to. Lastly, and I think most importantly for a lot of people, it's really when it's integrated with the ADS workbench, you really do not need any IT support, right? The ADS workbench will take over the process of calling up the infrastructure. It will take over the process of securely transferring the data, monitoring the simulation, transferring the data back, and then deleting the cloud infrastructure when it's done. Okay. There are many, many really interesting use cases for this the cloud, right? Especially for a small business like ADS. In order to compete with the larger general purpose CFD companies, we use the cloud extensively in order to do simulations that normally would not be available to us based on our infrastructure. One of the use cases of Cloud Leo would be, for example, in generating a centrifugal compressor map. In this example, we are generating the compressor map for the NASA CC3 centrifugal compressor. This requires about 40 points over 5 speeds, okay? And in total, it required about 240 cores. If I were running on this laptop, I'd really have to run all 40 simulations in serially, and that would really define the overall turnaround time for this compressor map. But with the cloud, I can call up all 240 cores, run the simulations in parallel, and get the results in about 2.5 hours. Okay, the overall computing infrastructure cost of this was $90. Another very interesting use case for the cloud is when we talk about unstructured meshes. Unstructured meshes have this notorious notoriety because it typically, for a level of granularity compared to a structured mesh, you need about 3 times the number of elements. Okay, meaning that the overall memory utilization, the overall turnaround time for unstructured meshes is much larger. But the advantage of unstructured meshes is pretty evident in the fact that the mesh generation process can be automated, and you can remove part of the man-in-the-middle issues. So what we have here is a dense unstructured volute mesh, which is consistent of 6 million elements. We partitioned this mesh into 16 blocks and ran it for 20,000 iterations. It completed in about 10 hours and cost us about $20 in infrastructure. The really interesting thing about unstructured meshes is we can continue to partition it from 16 blocks into 64 blocks or 128 blocks. And really that will reduce our turnaround time to, in a linear scale. What's also interesting is that there's a possibility that the overall infrastructure cost will not increase or actually decrease because of improved utilization of the cloud infrastructure. Okay, so it's really interesting now. You can spend the same amount of money, and now you can define what your turnaround time is going to be. Okay. Another very important use case of the cloud is for large-scale unsteady analysis or full wheel analysis. A lot of people are turned off for running full wheel analysis, even though it has the highest level of accuracy in a RAN simulation. It's just simply takes too long and requires too many processors, right? But with the cloud, it really enables you to call up the number of processors that you need in order to run one of these simulations. In this example, we have the Notre Dame high lift turbine, which is a 1.5 stage turbine and is made up of 165 passages. We split it up into 1/5 of a full wheel, but analyzed it for 1 full revolution. In this case, that was 10,500 time steps at 20 iterations per time step. Compared to a steady simulation, this is about 200,000 iterations in total. This configuration was made up of 10.6 million elements and was partitioned into 160 blocks. Again, normally we wouldn't be able to run this case. But with the cloud, we're able to call up those 160 cores and turn around the simulation in under a day. So now I want to talk about on-demand pricing. With the cloud, with this on-demand hardware, it really doesn't make much sense to have the on-demand hardware without an appropriate software model. And ADS is not blind to that. We've implemented this metered pricing approach that enables you to pay only for the simulation hours you use to go along with the Cloud Leo infrastructure. So I want to go through some of the highlights of the metered pricing approach. First, the metered pricing approach works both on your local computers and on the cloud. Okay, so you're not limited to, you can meter all of your simulations. Second, any simulation under 2 minutes is free of charge. And that is typically any simulation that is incorrectly configured, or 2D simulations, for example, when you're doing the section analysis during the fast design loop. Okay. With on-demand pricing, and there is no limit to the number of concurrent simulations you run. Okay, there's no job limits. There's also no limitation to the amount of parallelization you do. So really, with this, you have the ability to determine what your turnaround time is going to be. Okay. Uh, Additionally, you can share licenses amongst your team. And again, simulations are charged per solver hour. You're not charged for the time you're generating the mesh, and you're not charged for the time where you're analyzing the results of the simulation. Okay. Next, the rate per solver hour can vary depending on your expected usage level. Now, this is a really important point because I think the main takeaway here is, let's say you're a small business, okay, and you're in research mode, meaning that you don't have a particular business to take, but you still want to try and build that book. So you're doing research, you want to invest as little as possible and do only the simulations that will build business, right? You can pay a little, but have a higher rate per solver hour, okay? But once you get the work, once you get the design, once you're in the design process, you can change your solver hour rate to a lower level, but that's in conjunction with the work that is made available to you, right? So no longer do you have to predict how much work you'll have when you buy your software. Now you can scale your IT budget as work comes to you, okay? On the left, I want to show you I want to emphasize a point. There are two ways that people can manage their IT budget when it comes to CFD. Traditionally, you have two ways. You have some scenario which requires the most simulation power. That we call your peak case. You can build your IT infrastructure and your software hardware budget to fit this peak case. But unfortunately, what that leaves is a lot of room where there's a lot of waste. Okay. The other option is you set your IT budget to your mean. Okay. But what that prevents you from doing is doing those simulations that require more hardware or more software. And that really limits the amount of predictive accuracy that you can have or the turnaround time you have for your designs, right? But with Cloud Leo, you can get to determine anything. You can set your usage to your mean and then use the cloud for burst. You can use all cloud execution and just run it as you need it. Right? With this on-demand pricing in the cloud, you really have a lot more flexibility. Okay. I want to take a little time to acknowledge our supporters. We've been very lucky to have received 2 SBIR Phase 2 awards from the U.S. Air Force Research Laboratory to develop advanced turbomachinery applications for CFD. Currently, our first SBIR Phase 2 award was to develop an advanced conjugate heat transfer capability for cooled turbine applications. And we are currently working on another Phase 2 award to develop a fluid structure interaction module for high cycle fatigue analysis. I'm going to kind of finish up this talk by pointing out a few things that people are saying about our software. I want to point you out to two things. First is the fact that our software is opening up new opportunities to the small businesses, right? There are a lot of consultants or small businesses just don't have the infrastructure that they need to compete against their OEMs, the OEMs that have thousands of machines. But with our software and our metered approach, they're able to get the hardware that they need and run the simulations to make them competitive. Next, I want to talk about how easy it is to use our software, or how quickly people can become proficient with it. The first is an example where students were able to get comfortable with the ADS Spoil Designer and use it to learn about the basic aerodynamics of turbomachinery. The second example is when engineers have utilized CFD in the past. In this example, it took only about 2 to 3 hours of training for those engineers to become productive. Okay. Lastly, I would want to point you to a few case studies that we have online. These are available for download at www.aerodynamic-solutions.com/help/download/case studies. I recommend you go there. You can see what we've been working on, what people are saying, what we're doing. Okay. And with that, I have time for questions. If you want to talk to me in private, please, you can either give me a call or email me at info@adscfd.com or aerodynamicsolutions.com. And with that, thank you for your time, and I appreciate you coming and learning about my company. Uh, Thank you again.